Okay, on this video, we're going to learn about ballistics pendulums and how they're solved for using both conservation of energy and conservation of momentum methods, both within the same problem. So let's look at our experimental setup here. We have a mass of some type of putty here. So I labeled these the same on both. So let's call this MP. So we got this putty coming in at an unknown velocity, and it has a mass of 25 grams. Okay, and it's going to strike a pendulum, this block here, that has a mass of 0.7 kilograms, and it's on a string that's 1.2 meters long. Okay, after the collision, the putty is going to stick to the block, and the block is going to swing up through an angle of 21 degrees. Okay, and they're both going to be stuck together after the collision. When we're solving for these types of problems, and when we're dealing with energy conservation and momentum conservation type problems, you have to understand through any type of collision, the momentum's always going to be conserved no matter what. Okay, but this is an inelastic collision because they stick together. And we know that we're going to lose some kinetic energy in this collision. Energy is going to be maintained, but we're going to lose some energy to heat and other forms. So we can't use energy conservation methods when we're discussing the actual impact of the putty on the block. Okay, but what we can use energy conservation methods for, if we're assuming this pendulum is going to swing from here to its highest height, then the only thing that's acting on it, the only force that's acting on it during that part of the motion is going to be gravitational potential energy at this point. So basically, all of the energy after the collision is going to be stored in kinetic energy. Whatever's left, there's going to be some lost. But whatever energy is, whatever mechanical energy that is left after the collision is going to be stored in kinetic energy at that point, and then it's going to swing up through its highest point. Okay, so the first thing we need to do, since we're looking for the velocity of this putty, we're going to have to work backwards through the problem. So we need to start over here and figure out exactly how high this block is going to swing up through before coming to a stop, okay? Because at this point, all of the kinetic energy here has been transferred to gravitational potential at the highest location. So we first of all need to know this height. Now, we have a 1.2 meter long pendulum, and it's going to swing through 21 degrees. So what we have to do on this is make a right triangle, okay? And since we can't directly calculate this height, we can use trigonometry to calculate this length. We'll call this lowercase l, okay? So we can calculate this length and then subtract it from the 1.2 meters, okay? So height is going to equal 1.2 meters minus this L. If you notice, from this angle, this is the adjacent side. When this swings up through, the hypotenuse of this triangle is 1.2 meters. It's the same as the length of the actual pendulum itself. Okay, so we have the adjacent side and we have the hypotenuse. So height is going to equal the hypotenuse, so 1.2 again, but it's going to be cosine of 21 degrees. Okay, so we're going to put cosine of 21 there. So height is 1.2 minus 1.2 cosine of 21 degrees. And when we solve for that, it doesn't go very high. We get 0.0797. I think that's what I got. Yep. 0.0797 meters if we're going to stick with 368. Okay, so now we know the height that the pendulum went from the original state. Okay? And remember, gravitational potential energy is arbitrary. We can find any point that we want and establish that as zero. Okay, so the easiest thing would be just to say that at the resting state here, that there is no gravitational potential, and then at the highest state, it's going to have its greatest amount. So all of this energy here is going to transfer to gravitational potential. So the next step is to say that E initial equals E final. So 1/2 mv squared is going to equal mgh. Okay, now we've got to be careful about what masses we're going to be using. At this point, I know right here in this diagram, this block is just at 0.7 kilograms. But remember, for the conservation of energy problem, we are starting immediately after the collision takes place. Okay, during the collision, we're losing some kinetic energy, but immediately afterwards, whatever energy's left, we're going to maintain that through this motion to the highest point. Okay, so the mass throughout this entire problem is going to be equal to the mass of the putty and the mass of the pendulum for both of these. Okay, for both of these. So that means that it's the same mass, so it's going to go away. We can go ahead and cancel that out. All right, so we're looking for this velocity here. So V equals square root of 2gh. Okay, so our speed of the pendulum and the putty times 0.0797 meters. Square root that. The velocity of the pendulum and the putty is going to be 1.25 meters per second. Okay, now this is immediately after the impact. Okay, so now we're going to use our conservation of momentum equations during the impact in order to calculate this velocity afterwards. Okay, so same thing here. How many things are moving before the collision? So remember, momentum's conserved, so P initial equals P final. The only thing moving before the collision is the putty, so we're going to say mass of the putty times V equals, and then afterwards both things are moving, but they're moving at the same velocity, and anytime they're moving at the same velocity, we can factor out the masses and we can just say times V final. So we're going to say mass of putty plus, we'll say mass of our block, okay, times V final. All right, now this velocity that we just calculated here after the impact is going to be equal to, and that's going to be the final velocity now after the impact. Okay, so this was our initial velocity for this problem. This becomes our final velocity for this one. Okay, so we are solving for the velocity of the putty. So V equals, if we combine these two masses together, now be careful, this one's in grams. We have 25 grams and we have 0.7 kilograms. So if we move this 3 decimal places to the left, this is going to give me a total mass of 0.725 kilograms, okay, times my speed after the collision, 1.25 meters per second, and then we're going to divide that by the mass of the putty, okay, so it's got to be in kilograms, so 0.025 kilograms. And that's going to give me a fairly significant velocity. We end up with 36.2 meters per second. So this thing's moving. So this putty has to move at quite a speed before the impact just to get this pendulum to raise only 7.9 centimeters. Okay, so it's not going to raise it very far. So you can imagine it would raise it a little bit further, or of course the mass is going to determine this. But if we were trying to measure the velocity of a bullet coming in, okay, we could butt the barrel up to a ballistics pendulum and fire it, and then make the bullet embed into the block and allow that to swing upward through the motion, and we can calculate the velocity of a bullet, which is going to be significantly higher than 36.2. Okay.